All right, let's go on a journey. Think of it like a scientific detective story. We're going to uncover the fundamental building blocks of, well, everything. The chair you're on, the air you breathe, even you. So let's dive in.
I mean, that's a pretty wild question, isn't it? The idea that this entire solid, visible world is built from particles so ridiculously small, they're basically invisible. But that one idea, that's the seed that grew into all of modern chemistry. And you know what? It didn't start with a microscope. It started with just a thought. Way, way before we had labs and test tubes, this story begins in the minds of ancient philosophers. They were just wondering, if you take a piece of something and you cut it in half, and then you cut that half in half, what happens? Do you just keep cutting forever and ever? Or do you eventually hit a point, a final piece that you just can't cut anymore? Now, what's so incredible is that two brilliant minds in totally different parts of the world came up with the exact same conclusion. Over in India, Maharshi Kanad talked about Parmamonu, the smallest, ultimate, indivisible particle. And in Greece, a guy named Democritus coined the term atomos, which literally means uncuttable, an indivisible building block for all of reality. Two cultures, same incredible idea. But that's all it was, right? It was a really powerful story, a philosophical hunch. There were no experiments, no way to actually prove it. So for more than 2,000 years, the atom was kind of like a ghost, a really cool story, but with zero hard evidence. That is, until the 18th century, when the detectives finally showed up on the scene. So let's fast forward to the late 1700s. Scientists like Antoine Lavoisier and Joseph Proust are starting to do these really careful experiments. And they're noticing that matter, it doesn't just do whatever it wants. It behaves in very specific, very predictable ways. And just like that, they'd found the first real clues in our mystery. The first clue was a big one, the law of conservation of mass. And it's actually a pretty simple but totally profound rule. It just means that if you start a chemical reaction with, say, 10 grams of stuff, when it's all said and done, you'll still have exactly 10 grams of stuff. Mass doesn't just disappear into thin air. It just changes its disguise. Nothing is ever truly lost. Then they found a second clue, and this one was even more mysterious. It's called the law of constant proportions. Basically, it says that any specific compound is always made of the same elements in the exact same ratio by mass. It's like the universe has a super strict recipe book, and it never, ever deviates. Just look at water. It doesn't matter if you get that water from an iceberg, from a puddle in your backyard, or if you make it in a lab. The mass of hydrogen to the mass of oxygen is always in a 1:8 ratio. Always. Every single time. Same for ammonia. The ratio of nitrogen to hydrogen is always 14:3. It's a universal law. So you can see the puzzle these scientists were facing, right? You can't create or destroy mass, and all these chemical recipes are totally fixed. But why? What is it about matter itself that makes these rules true? All the clues were right there on the table. They just needed a brilliant detective to put it all together. And that detective's name was John Dalton. He was an English school teacher, and he's the one who took that 2,000-year-old philosophical hunch about atoms and realized, wait a minute, this is the key. This ancient idea is what unlocks the whole mystery. And get this, Dalton came from a poor weaver's family and started teaching when he was just 12 years old. This guy was a brilliant, totally self-taught mind who just loved to research. And then, in 1808, he presented the theory that would become the absolute foundation of all modern chemistry. Okay, so Dalton's theory was built on a few really powerful ideas. 1, everything is made of atoms. 2, you can't create them or destroy them. And 3, each element, like gold or oxygen, has its own unique kind of atom. And these different atoms combine in simple, whole number ratios to make everything we see around us. And boom, just like that, the puzzle was solved. Why is mass always conserved? Well, because chemical reactions are just atoms rearranging themselves. You're not creating or destroying the atoms, you're just shuffling them around. And why are the proportions always constant? Because a molecule of water is always made by combining 2 hydrogen atoms with 1 oxygen atom. The recipe is literally baked into the atoms themselves. So with the mystery solved, Dalton's theory became way more than just an explanation. It became a toolkit. It gave scientists a whole new language to describe the world, and even to build new things. But of course, this amazing new language came with a brand new challenge. So the theory says Every type of atom has its own special mass. That's great, but it immediately leads to a giant question. How on earth do you weigh a single atom? I mean, they're unimaginably small. You can't just pop one on a scale. The solution scientists came up with was incredibly clever. They just created a relative scale. Instead of trying to figure out the actual absolute mass in grams, they decided to just compare everything to one standard. And that standard became the carbon-12 atom. They defined one atomic mass unit as exactly 1/12 the mass of one of those carbon atoms.
Okay, think of it like this. Imagine a fruit seller who doesn't have any weights for his scale. What could he do? Well, he could take a big watermelon, declare that it weighs 12 units, and then cut it into 12 perfectly equal pieces. Now each piece is 1 unit. He can use those pieces to weigh all his other fruit relative to his watermelon's standard. That's exactly what chemists do with atoms, using carbon-12 as their watermelon.
So, knowing an atom's relative weight is one part of the puzzle. But how do they actually, stick together to make molecules? That's where this idea called valency comes in. The easiest way to think about it is as the combining power of an element, like the number of arms an atom has to link up with other atoms. And that number is what determines the rules of the game.
And valency gives us this really simple trick to figure out chemical formulas. So let's take magnesium and chlorine. We write down their symbols, and then we write their valencies, or combining power, right above them. Then you just crisscross those numbers, so they become the little subscript for the other element. And just like that, you get the right formula for magnesium chloride, MgCl2. It's like we're learning the grammar for this whole new chemical language.
In the end, it really is just like a mason building a giant wall. He uses these small individual bricks, one by one, to create this huge, impressive building. Well, the universe does the exact same thing. The building blocks of all matter, the absolute bricks of reality, are atoms. They're the unseen foundation for literally everything. So we went from a simple philosophical hunch all the way to a predictable science that lets us build our world, from medicines to new materials. It really makes you wonder, doesn't it? What other huge, world-changing truths are still out there, just hiding, waiting for us, right beyond the edge of what we can currently see?